Welcome, everybody, to Rancher Government Solutions monthly webinar series. Today, we're going to talk about air gapping Rancher made easy with Harvester and Terraform. Leading our discussion today is the talented Brian Durden. Brian is a field engineer with Rancher Government Solutions that started out as an embedded developer and worked his way up to the cloud to become a full stack developer and architect. He specializes in enterprise-ready, suitable automation patterns for Kubernetes and various cloud on-prem infrastructures for federal government customers and their missions. So without further ado, Brian, take it away.
Hey, thanks, Don. I appreciate that. So yeah, I'm Brian. I'm a field engineer with RGS, and I kind of have a passion for the Kubernetes stack. And a lot of the places I've had a job at, I've had the fortunate opportunity to be able to dive in and kind of build a mad scientist role. So RGS has also given me that opportunity, and I've been really enjoying it here. So what we're going to go over today is how we air gap using RKE2 and Rancher Multi-Cluster Manager into our Harvester HCI. I am running Harvester HCI on my device here. This is a Minisforum HX90. It's running a Ryzen 9 CPU with 64 gigs of RAM and just a regular SSD in there, nothing super special. But the cool part, and the part that everybody is probably looking at right now, is the GPU that is sitting on top of it. That is an MSI, that is a GTX or RTX 3060, 12 gigs of RAM, and it is using a PCI Express ribbon cable that goes under the box and mounts to an external board here that plugs into the M2 slot. That's a lot of word salad. Don't want to dive into it too much. If you want to see this guy in person, come see me at one of the conferences we're going to mention later, and we can break the whole thing down and talk shop over that. But I'm going to run Harvester on top of that because the Ryzen 9 has a lot of cores, 8 cores with 16 threads. And so I can run a virtualized environment on top of this single box, and that's what I'm going to demonstrate on today. So let's start off. So I like to start off in conferences where we have kind of a common language that we kind of settle on, because in this industry, in the tech industry, there's lots of ambiguous terms out there, and there's lots of word salad and like I call business bingo words that mean different things to different people. So we're going to start off with the idea of we're talking about air gaps. So let's level set what an air gap actually is. So air gaps are, as we said, it's very ambiguous around the tech industry. It means different things depending on who you talk to and their perspectives. And I kind of thought of it, it's a very good analogy. It's as the word barbecue around the world. If you've ever traveled internationally, barbecue in the US means a thing, and barbecue in, say, Europe means a very different thing. And for the record, barbecue in the US is the correct usage of the term. It's not like I'm biased or anything, but barbecue, it does not mean cooking on the grill. Barbecue is a style of cooking that involves a grill. There's a subtle difference there. But anyway, depending on who you talk to, air gap can mean something very different. And it's very important that we kind of level set on that, because when we build these solutions for our customers, the minute differences really come into play, because the closer you get to the real production solution, the further you move away from like kind of a generalized pattern. So we're going to keep it simple. We're not going to dive into all the different minutia of air gaps, and I'm going to play up to a food analogy again. We're going to go with hard air gaps and soft air gaps, just like tacos. And I'm biased, but soft tacos so much better than hard tacos. Just a level set there. Okay, so moving on. Oh, there's an error here at the top of the slide. My bad. So we need to pick a side for our air gap. Just for the record, on this demo with this box, I'm doing a soft air gap. I technically do have internet connectivity, but I do not have dependency on that internet connectivity. It's there just to make things work smoother, and because I'm hooking my laptop up through it, I can pull stuff down onto a web page and that kind of thing. So a hard air gap, the name is kind of self-explanatory. It's a physical, like real air gap, to where it is two complete separate networks. It is not connected to, say, the public network. It's not just that, though. It's also a strong process and security controls around the actual physical access to that network. So if you've ever been in a SCIF environment, you know there's a security officer there that kind of says, yes, you can come in, no, you can't come in, you got to have a badge and all that stuff. So they really control physical access within that environment. and services internally like DNS and DHCP and say authorization providers, public key infrastructure, things like that. That is all internal. That has to be because there's no external connectivity. So all that stuff has to be provided within the system. Because of that, flexibility is very limited. Sometimes you just can't do stuff in those kind of environments. It's like, hey, here's this great commercial cloud solution, and you can't use it. And that's just the way it is. Also, there's lots of controls around what kind of software can be brought in. I won't even go into that subject, but that one's pretty well known. So with the soft air gap, this term's a bit more ambiguous, but generally there's no physical gap. The gap is usually software defined to separate these environments. We have a thing called VLANs, software defined networks and virtual private networks and robust firewalls, depending on the architecture. That's really what enforces your gap. The internet access may be present, but if it is, it's usually heavily regulated using access control lists and allow lists and things like that for, like, say, sites you can actually connect or ports you're actually able to connect over, banning different protocols and things like that. Jump box and bastion hosts are usually very common, but we also see to where you can use your own workstation over, like, say, a VPN with some zero trust setup. And just connect right in. And that's kind of what I'm going to do here. I'm not going to dive into the implementation of that because honestly it's a little outside the scope of what we're going to go over. But let's see. After this, we're going to talk about the air-gapped demo network. Now, I'm describing all these things because it's important for you to understand the context behind what we're air-gapping and how we're doing it. So I'm doing it in a way. Somebody that might want to reproduce in their own environment will have a different set of controls or a different set of, say, completely different hardware or a different network. And you need to understand where the pieces go so you can actually kind of reproduce this system. So as we arrive at this slide, there's something else I want to talk about real quick. We need to, again, agree upon a verbiage for how we describe things in these kind of cloud and on-prem architectures. So I've worked with a lot of different customers and they have different ways of describing it, but I think the most common way of describing one environment that is mostly self-sustaining, that may have multiple workloads or teams or whatever working in it, we generally describe that as an enclave. I have also heard it described as an estate, where each, workload or network or something like that becomes a foundation on an estate. But the enclave verbiage seems to be a little bit more common. So that's what I'm going to go with. Usually most enclaves are kind of defined by like a single control plane. A control plane being a place you run your automation from. It may also host, say, Git repos or your image repository, like a Harbor or Docker Hub, like on-prem or something like that. Having a single control plane to automate those things is it's a good pattern to follow, but doesn't work for everyone. So I'm explaining my solution here, and we're going to kind of follow that. But you can kind of keep in your mind maybe your environment's going to be different, so your solution may be a little different here. What I have here in the air-gapped demo network is kind of mostly managed, at least network-wise, by my travel router. You can see it in the screen here. It's over on the left-hand side. This is the GL iNet travel router. It's a Slate AX for those that are curious. It runs OpenWRT. It allows me to do a lot of really cool stuff that you normally can't get even out of like home routers, and I can take it with me to trade shows and stuff. I have defined several VLAN-based networks within the OpenWRT environment, and each of those has its own DHCP. DHCP allows me to basically dynamically assign IP addresses and other things to hosts that are connecting to it, and it greatly simplifies like setting up many workloads or virtual machines or things like that are running within an environment. I have 4 different networks set up on it. I have a services network, sandbox, dev, and prod. In this environment here, where we're just testing like bootstrapping, RKE2 and Rancher, we're just going to use the services VLAN, but I wanted to highlight what I have set up and that this is very flexible. Harvester, on the other hand, is based on, it is Kubernetes, it is RKE2 running on a SLES 15 implementation, and the difference is it uses KubeVirt to manage virtual machines within Kubernetes and leverages Longhorn for spanning storage. So within that, I'm able to map networks based on VLANs within the Harvester environment, and then the travel router functions as my top level router to ensure that the networks are defined and routed accordingly. I have no switch here. I only have 2 ports plugged into this thing. And just for demo purposes, that's plenty fine. But I mean, in a real environment, you're going to have a much more complicated setup than this. You'll probably have a top level switch that manages a lot of this versus your router. But let's not dive into it too much. So Harvester itself is running on the untagged network. It's just the 1010/24 is all it is. But the other 4 networks that are running are like variations of the VLANs or whatever. So, all right, so we're going to move on. Okay, so I'm going to show here, this is the Harvester internal networking diagram. And we're not going to walk through this too much, and I don't mean it to scare anybody by being too technical. But what's happening under the hood is Harvester is basically mapping these VLAN-based networks to the virtual machines when they run. This allows me to spin up a virtual machine and declare what network I want it to be on. And then when it comes up, in this case, I'm going to be using Ubuntu-based images. It will acquire an IP address and work from there. And that IP address will be in the range that we just went through. So we're going to jump into air-gapped principles and patterns here. So for Rancher itself, there's several different dependencies that we have in place. So in order to get Rancher into an actual air gap, there's key dependencies that you really need to consider ahead of time. So there's a little bit of planning involved for getting into your environment. It's not a whole lot of things, but it's things that have to be considered nonetheless. So the biggest one, and this is a Harvester dependency issue, and if you're using something else like vSphere on-prem, for instance, you'll also have to consider the issue of VM images. When you are in an air gap and you have no internet, you need to have pre-built VM images that have all the binaries on them that you need. There's ways of getting around that by mirroring, say, for instance, Ubuntu's package management aptitude. You can mirror that internally. So that's a solution. In my case, I didn't want to go through that effort, so I just went and built some VM images that have ARC82 and all the binaries and everything I need on them to bootstrap it. And those images I pulled down as part of the Terraform bit that we're going to go into later. So one of the other things is container images. Container images, Kubernetes is a container orchestrator at its heart, so its intent is to run containers at scale across many environments. And because of that, we need all the container images that we have dependencies on, for, in this case, say Rancher and Cert Manager and all the other things that are running on ARC82, they have to be available inside of an image registry. And that image registry has to be within our air-gapped environment, because if we're not reaching out to the internet to, say, Docker Hub, or say Quay or something like that, then we need the ability to pull them down internally. So that's one of the things. You need a place to put that there. Classically, that is called an image store. When we bootstrap, usually we'll reference the image store in some manner, and things get pulled down and magic happens and everything comes up. So the next bit is the actual bootstrapping of the environment. So this is something we've heard many people talk about before. It's basically a chicken and egg problem. So having everything in an environment to where you can bootstrap it is one thing, but it's the actual aspect of creating it from that source at the same time that can become kind of a chicken and egg. So you want to avoid some kind of circular dependency there, because if you have it, you can't actually do anything. So we need to be able to boot an environment up by using the same and consuming the same images that we're providing for future provisioning once we're actually up and running. Because as you know, Rancher's multi-cluster manager allows us to manage many clusters over an infrastructure or many infrastructures. But to be able to provision those clusters and the applications that run upon them, we need to pull those from an image registry. So we're kind of self-dependent on that registry. So we got to have a method of getting that in there. And that's typically called the bootstrap. With our VM images, we have the binaries on there that we need. So typically we can just spin up a VM with that and run them, and we're okay. And that kind of leads into the next bit, which is basically the provisioning code. That can be Terraform, Ansible, any kind of infrastructure provisioning code that you like, even Cluster API if you're that advanced in the Kubernetes side. Something there to actually provision your environment. So with that, we have built that out for this environment, and everything is running kind of self-sustained on this box, and all of that is available. So what I'm going to do now is we're going to talk about manual provisioning first. So the automated provisioning, which is basically the purpose of this demo, is going to go by so fast that you may be wondering what happened, because it literally takes 5 or 6 minutes and we're done. And that's bootstrapping a whole environment. So that's pretty cool. But the thing is it's more of an educational exercise to walk through exactly what's happening and why this automation from a deterministic point, where we're defining it infrastructure as code and then building out that environment declaratively, is so useful and so important. So as you know, manual provisioning, like pointing and clicking and copying and pasting and all that kind of stuff, is like super toilsome. There's lots of wasted time. It doesn't scale. And honestly, like platform engineers and DevOps folks, DevSecOps folks, they're too talented to do this kind of work. They shouldn't be pointing and clicking. They shouldn't be copying and pasting. They should be spending their time diagnosing hard issues and improving the product, improving the features, fixing bugs, that kind of stuff. So we'll go through why it's toilsome and then step back, and then I think we can fully appreciate why automating it is just so much more useful from the get-go and right out of the gate. So if we go through the steps at a high level, we're looking at the first step is VM image creation, which is like the base image that we talked about earlier, and then importing it into our environment. The Kubernetes binaries and other dependencies, anything that you need, either needs to be on that image or it needs to be available within the environment. Follow that up, we have to get all the container images defined in a manifest, manually pull them down, put them into, say, a tarball, and then push it into the air gap environment. And then what that looks like, it might be on physical media if you're on a hard air gap, or if you're in a soft air gap, you might just be copying it to a different network from like a jump box or something like that. It really depends. After that, you have to provision your VM networks or your instances. When you provision the VMs, generally you're mapping it to the images that we just talked about, as well as the networks that we went over a few minutes ago. After that, VMs are now running, good. Now we have to hop on the VMs, and now we have to install Kubernetes, creating the control plane node or many control plane nodes, joining them together, and then joining the workers as part of that package. And if you're scaling out to, say, a big cluster, like, say, HA control plane with, say, 6 workers, you're talking about 9 VMs that you're having to manually go in and set up. And that is just a huge headache that no one wants to do. So, and then after that, as we're bootstrapping Rancher, we would have to install the Rancher application on top using, like, say, Helm. But that's still yet another manual gate that you're having to type in code, and scriptifying this can kind of help, but we really need provisioning tools that allow us to describe these environments in kind of a declarative way. So for a thought experiment for the audience, what does that process, this manual process look like that we just went over, look like when you need to upgrade? And I'll let you think about that for a second. So all these manual gates and these copying and pasting and everything, if I need to upgrade this environment, what kind of like artifacts and stuff do I have to have process around to handle, which just gets really difficult, that might be improved if we had a lot of automation in place. So I think that one kind of bears out. It doesn't really need too much repeating. I think you can understand the difficulty there. And if anybody has any questions in that regard, we can dive into that, because this is really where differences lie for the environments that we see. All right, yeah, so if anybody has any questions about manual provisioning or any of these other subjects, we can talk about it at the end. We're going to have some time for Q&A, and we can dive into this. And again, I'm going to be at a bunch of different shows, so if you're going to be there, come see me and we'll chat about this stuff. Happy to talk shop. All right, so bootstrapping. Bootstrapping is the initial creation of the cluster that we're going to run Rancher upon, and I'm going to go over that process. So there's some things you're going to see, and there's some things that you're not going to see. So what you're not going to see, I'm not going to show you the VM image creation and import. Honestly, that's boring. There's lots of different ways to do that too. You can use a very mature tool like HashiCorp's Packer, which a lot of you have probably heard of. You can also use, what I did is like super simple. I used the KubeVirt, the GuestFS tools, to just take an Ubuntu image and just plug some stuff into it, and then, voila, I'm done. We're not going to dive into container image importing, which is basically pulling down 30 or 40 gigs of containers and importing it into my environment, because again, that's boring and kind of out of the scope of what we want to show. Both of these cases that we're talking about and how I did it in this environment is extensively covered. We're going to share a GitHub repo at the end of the presentation, and you can pull down all the code and everything that I'm using. And there's some docs and everything as well, and it dives into how to do a lot of the stuff that I've done and being able to repeat it. And also, we don't cover the installation of an image registry. In this case, I'm using Harbor. I'm running it in Kubernetes on bare metal on Harvester because Harvester is Kubernetes at the core. But you could also run it as a virtual machine, or even not in this environment. You have it external. Sometimes there's legacy systems, and you're kind of inheriting a system already. So maybe you're running Artifactory or Nexus or Harbor, and you have to use that. This is where you would put the images. I'm not going to cover that as part of this. What you are going to see is we're going to walk through the Bootstrap code, the cloud on it specifically, and talk about how it functions. We're going to walk through the Terraform code to show the declarative state for infrastructure and how it's all brought together. We're going to talk about dependencies and variables and some of the Terraform idioms and how that works. And then we'll see how the installation of Rancher 2.7.0 on RKA2 works. And then at the end, if we have time, we're going to do a create run of a downstream RKE2 cluster on this environment. So we're going to have Harvester, and then we're going to install Rancher on top, and then we're going to make Rancher to where it can provision more clusters into Harvester, which is kind of a cool pattern. I'm a fan. All right, so let's hop over into the fun stuff, and we'll dive into the Terraform code. All right, so one of the cool parts about Terraform is it allows you to black box specific components, so you don't need to know how they function. It also allows, like, say, other teams to go write these functions. Or even further, there's another thing called providers, or a Terraform provider. And we are actually leveraging a Terraform provider here. The Harvester team is awesome, and they have their own Terraform provider, and I use it here because a Terraform provider allows you to create structures or objects within that environment that are unique to it. So the Harvester provider allows me to create Harvester virtual machines, Harvester images, and things like that. We can pull up here and go have a look at Terraform Harvester provider. My typing is terrible. And you too can see this, so that here we can go to the documentation, and this comes in and tells us all the different resources that we can create, and then the values that they need, and then you can also use them as data sources for exporting things. It's pretty cool. I found this super useful. I'm a big fan of Harvester, I'm not going to lie. But let's jump back into Terraform here. So here I declare the provider that I want, and we won't dive into too many of the specifics here because I don't want this to be a full Terraform education bit, but I'm declaring where I want my state stored. So when you run Terraform without a backend defined, it'll just store the state locally, and that's fine, but I typically work between multiple laptops, so this is actually telling Kubernetes to store the state in my cluster. So my cluster becomes the central source of truth for that information, and it just makes it a lot easier to work with. These backends you can also set up to be like an S3 bucket or something like that. Working with teams on top of a single Terraform deployment, you definitely want the state stored in a single location because Terraform also provides a locking mechanism that prevents others from actively terraforming while you are using the tool. That way you don't have any kind of crossover when you're creating environments. And part of the power of Terraform is it allows you to kind of declare the environment that you want in a declarative way. Yep, I used the same word in the same sentence there. What that means is you can describe an object at rest and say, here's the components. These are the configurable items that I want in it. Say for a virtual machine, you might have a host name, maybe the network interface that it's connected to, disk space, CPU power, that kind of thing. And now you've described a virtual machine by that name. And when you run Terraform, if that object does not exist, Terraform will go create it. If that object exists, but you have changed something, Terraform will go change it. If you want to destroy it, or maybe it's not there anymore and you've removed it, Terraform notices it doesn't need to be in there, so it will go destroy it. Be careful with that last one because it can bite you. So moving into all the different components here, I don't want to go too deep, but I said it's black box, and if any of you are actual developers, you know how classes and things like that work. So this is kind of where we define our variables for all the different objects that we're going to have. We can, basically all the types are generally strings. Doesn't always have to be, but I tend to stay with strings because they're easier to manipulate if you're using any kind of external scripting or make files, which I'm a fan of. And within those variables, usually you have either a default And if you don't have a default, you need a way of actually defining it. And that brings up a Terraform's TFVARS file. And in this case, this is just a template. And typically what happens is this is what you commit to your GitHub repo. And the TFVARS file tends to have secrets in it sometimes, so you don't want to actually commit this into your Git repo. And you can tell it's grayed out, and that means I've actually got it in my Git ignore. I do not allow that file to get committed by accident. I'm not a fan of secrets in Git, so we tend to avoid that. And in this case, I've got all the variables filled out for what I exactly need. All right, so almost done. This is the virtual machine. This is a Harvester virtual machine object. I'm declaring it as a resource, and I'm giving it a name. And you can see here there's some $ with these braces surrounding it. This means that it's an actual variable name. So my host name, CP host name, is actually a variable. And if we go look at that and pull it up, it's right here at the top. It has a default, and I call it RKE2 airgap CP. But if I wanted to, I could actually override that by putting it in TFVARS and just overriding it. But I'm gonna leave it alone because it's not super important. It just needs to be common. So walking through, this is a typical virtual machine. We're defining 2 CPUs, 8 gigs of RAM. Here's the host name again. And then I have no SSH keys explicitly linked because I like to use those in the cloud init, which we'll get into in a minute. And then I have a network interface defined here. So this network interface brings up one of the other types of objects in Terraform. Instead of a resource or something we're going to create, this is how we reference something that already exists. In this case, it is a Harvester network, the services network that we went over in the slide deck, that already exists in my Harvester environment. So when I go to data, I like to put everything in a data file. These file names are entirely arbitrary, but they're more to allow me to kind of visually see, yes, the data objects go in data, the image objects go in image, any keys I need to generate go in keys, and so on. So it's a little bit more organized for me and let me visualize it. You could just throw everything into one big file if you want to. That's generally not advised, though. It's not a good idea. But in here, I'm referencing it's a Harvester network. I call it services, and then the actual reference name is services under the hood. And then when Terraform runs, it verifies that this data object exists. And then if it does, it pulls the information that it needs for it. And in this case, I'm literally just getting the ID of the network that I'm connecting to, just so I can reference it saying, hey, I want to bind my network interface to this network when I start, and that's it. We could have many network interfaces if we want to, but in this case, we just have one. I have one disk defined. That disk is going to be the Ubuntu RKE2 image. Let's go look at that. Now in images, this is telling me that I need a Harvester image, and a Harvester image is a virtual machine image. We've gone over this a few times. This is the one I went and built ahead of time. So this image is literally just Ubuntu 2004 or Bionic. It has the RKE2 binaries downloaded to a specific directory. It has the official RKE2 start script that some of you may have seen before. That's actually on the virtual machine instead of actually referencing it from a cloud source. And a few other components like KubeVip. If you've seen that, I use that for static IP provisioning. All of that's kind of canned in the virtual machine. And this is basically referencing the name of it as a variable, and the name of it as the display name, and then the URL for which I want to pull it from. So in a real environment, you might have this image available within your environment at a different URL. That's why I make it configurable. I'm running it from my local environment. In fact, I don't know if you can see it on the screen, but I have a key drive plugged in right here. It's a 1 terabyte drive, and I have it shared on a little HTTP server on my laptop. And I'm basically self-referencing where the URL is coming from, just because it's convenient. For the details around how that works, the documents and stuff we're going to define or provide as part of the GitHub repo, that's all in there. It shows you how to do it if you just want to do it like kind of in a POC manner. But typically in the real world, you'll have this image saved somewhere, and it'll be version controlled and everything, and you'll be referencing that here. But in my case, I'm just kind of doing things for expediency. So back to the VM. Now we get to dive into where the rubber actually meets the road. This is one of my favorite places, and this is probably the reason I like Harvester the most, other than it being a Kubernetes base. Cloud init is the kind of a generic cloud mechanism for provisioning virtual machines. So you have a virtual machine image, and it's kind of static, but you need to give it a host name, you need to create network interfaces, you need to maybe install some applications or set permissions, add users, that kind of thing. Cloud init allows you to do all of that from a kind of a YAML point of view. So you can define a YAML file, And then that YAML will basically define all the stuff that's going to go into the virtual machine. So Cloud Config and Cloud Init, they have their own like format, and you can go look this up. There's a huge amount of documentation and examples on how to do this. This is just how I have mine set up. So on RKE2, if you've ever installed it by itself, there's several different ways of doing it. The way we're working with is the official install script that is available on the GitHub release page from Rancher. Here we are defining the config YAML file and defining basically a token. Now this token is just kind of generic, but in the real world you'll want something that's not guessable. And here is where I'm actually referencing the image repository that I'm storing all of the containers in. So this is under system default registry, and this ends up being just, it's my Harbor URL that I have defined. Under TLS SAN, this is where I force multiple subject alternate names, or SANs, into the certs when they're generated. This is just one of the several startup features of RKE2. I'll have one that's defined for the host name, but I'll also have one that's defined for the master VIP. This is the virtual IP that I'm going to use as a static reference point for this cluster so that it doesn't change. It makes it easier to do DNS when the IP doesn't change, and so also when doing control plane HA, you need to have a common IP that all of the control plane nodes can actually reference around. Sometimes that's a load balancer. In this case, I'm just using kubevip instead. So in my etc hosts, I'm kind of bypassing the need to make some DNS entries, nothing special there. And then there's the registry's YAML file that RKE2 consumes. And this, again, is defining my Harbor registry that I have running. This is, if you've ever seen Containerd, this is literally getting injected into the Containerd toml. So down to the run command. So these commands are run when the virtual machine first starts. They do not run again. So they're kind of a run once, as we like to call them. And in this case, I'm starting up the agent. This is canned Harvester. It has this on all virtual machines. It needs the QEMU guest agent to inquire IP addresses and things like that. So I leave that up there. But then you can see here, I'm actually doing some commands that are going to go install RKE2. There's an install script. This is what we pulled down from the RKE2 release. This is where I stored all those binaries. I want to say it's 400 or 500 megabytes worth of stuff that is actually stored in this directory. And then I run a command for kubevip, and this generates a configuration that I need at runtime and spits it out into this, this VIP YAML file. And so I don't want to dive too much into Kubernetes, but it's a static manifest. So a static manifest means when the actual kubelet comes up on the node, any static manifests that exist on the node, it will run as pods, like immediately, or deployments or daemon sets, or whatever you configure it as. It's not something that goes through the API server, you know, with kube control, create, blah, blah, blah. Very different mechanism. And then now that everything's installed and running, I enable the RKE2 server as the control plane mode. When you're looking at RKE2 docs and you're looking online and you're seeing how to get this in your environment, this flow is the exact same thing that you see. The only real difference is that the files are located in the virtual machine now as opposed to pulling from the public cloud. That's literally the only difference. It's very straightforward and easy to work with. So won't spend too much more time here. The worker node is almost a mirror of the control plane node. From a VM configuration standpoint, I add 4 CPUs instead of 2, make it a little bit beefier. And down further into Cloud Init, it looks a little different. The main difference is this server line. This is basically telling it how to connect to the control plane node when it comes up. So it has the host name and then the port that it needs to connect to. And then you can see here the command to install RKE2 is a little different. We're adding in the agent tag, which means this is going to be a worker. It's not going to be a server. So when it starts it up, all the pre-configuration is just to connect as a worker. And then when we start the service here, that's what's going to happen. So that's pretty much the walkthrough for Terraform. One of the key points when working with Terraform is, especially in an air gap, Terraform is a cloud tool, first and foremost. So when you run it and you're initializing your environment, much like Git init, you do Terraform init. I'm going to do that here because technically I have internet. But in a true air gap where you have no internet or it's tightly controlled, this may not work for you. So you would need to prep this environment outside of the gap first, much like you've done for the virtual machine and the container images that you were, say, dropping on physical media or copying them over from a specific machine, however that works. You would need to do that for Terraform. So what happens is it creates these directories called .terraform and .terraform lock HCL. And there's tons of random information in here. But the point is now all these plugins, the providers and things like that are now available locally. So I can take this environment, zip it up, drop it, and now run it. And now it doesn't need to reach out to Terraform to pull any updates or the plugins because it already has them. There's probably more enterprise ways of doing that to where you can say, hey, I'm hosting Terraform providers from this location, but this is usually the quick and easy way that I've always done it. It just works well and usually no problem. So the next thing we want to do is before we actually do a zip up to bring it in the environment, we want to run a Terraform plan and make sure we don't get back any errors. And we don't. The plan allows you to store the plan to a file. Depending on your workflow, that might be the way you want to work. You want to output the plan and pass that plan over to, say, a lead DevOps or a lead platform engineer to maybe get some audit and just look at it and say, yep, that looks good. Or maybe even pass it into an automation system that goes through and makes sure nothing's amiss. After that, you can just do a Terraform apply. You can consume the plan that you created earlier, or you can just do apply and it'll create a new plan right then and there. We don't have no audit trail here. It's just me. So I'm going to run Terraform apply. So before I hit this, we're going to be switching back and forth between this terminal and a web browser so we can kind of talk through what's happening. So one of the things I haven't gone over yet, and I really need to, is the issue of dependencies with Terraform. So when you have Terraform code and you're referencing other modules or other resources or something like that in the system, Terraform builds a dependency map or dependency matrix of those objects and kind of builds a tree. And within that tree that it's built, it works its way through to where all of the dependencies, once you come to creation of a specific resource, have already been resolved. So in this case, the easy one is this is my virtual machine image that I need to copy into Harvester. That's obviously a dependency. I got to have that. So this is going to be one of the very first things that it creates. And that's a dependency because in my node here, I'm actually referencing this image right here on line 47. That's an implicit dependency. That's super easy. It's kind of intuitive in a way. It's not anything I need to worry about. Terraform's just going to take care of it. But what about the case to where there is no implicit dependency? It's more of an explicit one. So there's another phrase you can call depends on in just about every resource where you can say, hey, this object depends on another object. And in this case, it's the control plane node, the one we were just looking at. So in this case, I'm saying the worker node is dependent on the control plane node. And that means the control plane node has to be fully functioning and running before the worker can actually begin creation. And when Terraform walks this tree, it'll obviously find cases to where it can parallelize creation of resources because there's no interdependencies and they can just continue forward. So it does that automatically for you. There are ways to restrict the amount of parallelism that's going on, or if you just want to do single for safety, that's all configurable, but we don't need it in this case. Okay, so when resolving dependencies in Terraform, there's also the case of when is a resource created? So some resources are simple. In this case, we got an image. The image is created when it's been pulled down and it's ready. That's obvious. There's no complexity there. But what happens when we need a virtual machine created? Well, when a virtual machine spins up, how do we define when it's ready? This is kind of a pick your poison, or it really depends on your own solution on how that works. But for this case, and then with Harvester's Terraform provider, that is actually defined by the provider. The provider says when a virtual machine is ready, its IP address has been acquired, and it is the agent on board, the QEMU agent that we talked about, is running, and it is broadcasting an IP saying, hey, this is my IP. That is running. If we were just spinning up virtual machines and only configuring a virtual machine to sit there and static and not do anything, that would be fine. But we're actually creating a virtual machine and we're running RKE2. So the aspect of running RKE2, we have to wait for that to start up and for that to be ready. So there's several layers of what ready means on this virtual machine. So the way we do that is to get around this issue is, yes, when the node is ready according to the Harvester provider, that is fine. It is ready, but we add another layer by adding a thing called a provisioner. And in this one, I call it remote exec. And we're basically going to create an SSH connection to the actual VM and run a command on it. And when the command comes back clean, like good, that means it's ready. And in this case, this only runs after the virtual machine is started, and within the virtual machine, Cloud init is already running. So this provisioner has nothing to do with actually running Cloud init. But what it does is it actually pins on Cloud init with a wait flag and just waits for Cloud init to finish. And when Cloud init is finished, that means the actual RKE2 server is actually running. So that's actually a really good marker for when this thing is running. So that's why the actual provisioner is in here. And then I do the same treatment with the worker node, just for the same reason, in case we have any dependencies on the worker node, which we do. We have Helm charts. And those are defined in the Rancher Terraform here. These are just basic Helm charts. If you've ever run Helm before, do Helm install, blah, 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 Helm release, and then you actually show the Helm chart. These Helm charts are tarballs. They're self-referenced here locally. They're not pulled down from the internet, and I'm overriding some values in there. Same thing with Rancher. So back to the terminal. We've gone through all that, and so now that we know the dependency matrix, we can kind of assume what's going to happen, and we're going to see it scroll by on the screen. So I'm going to hit go. And everything came by, and now it's asking me if we're good. And it says 9 resources to add, and that's what I saw on the plan, so I'm going to assume that that's probably okay. And I'm going to hit yes. So we can see here immediately it created a SSH key right out of the gate. So yep, that's a dependency. We need that for our VM. And the next one is this Ubuntu RKE2 image. So it says it's creating that. So let's go have a peek and look at the images here. And oh, look at that. It's downloading the image automatically. That's pretty cool. It says the image full size is going to be 1.42 gigabytes, and the image it is based off of is this one at the top, which is 608. So that sounds about right for all the stuff that we installed on that sucker. And then once the virtual machine image is downloaded, then it's going to create virtual machines with this image as a base. And as we know, the first one's going to be the control plane node. And so what should happen is after this hits 100, we'll go back to the terminal here, and it should pop up saying, yep, I'm moving on to the actual virtual machine node. There it goes, virtual machine creating. So let's hop over into Harvester and look at the virtual machines. And yep, there it is. It is starting. You can see the age ticking by. So usually the virtual machine, what's happening under the hood, Harvester, especially if you have multi-node, Harvester intelligently figures out what node it wants to run the virtual machine on. And then it passes, if the base image is not available on that node, it does a copy to get it over there. And then it starts the virtual machine, and then it just starts, the virtual machine begins booting. In this case, the node flag is telling me, hey, this is on the Harvester node, which I only have one, so I just called it Harvester. But in another system, it might be Harvester 1, Harvester 2, etc. And it's already got an IP address. It's pretty fast. That means the router that we talked about has already assigned it a dynamic address. And on here, the actual Cloud init stuff should start. Yep. So what happened is it detected the actual IP address has been provisioned, so now it's moving on to the SSH provisioner that we talked about. And you can see it's attempting to connect over SSH, and it says connected. And it is now waiting for Cloud init to complete. This usually takes about 2.5 minutes for it to finish. So what's happening behind the scenes when running the install script is it takes all the artifacts that are available locally and then extracts them to like actual binaries, and it places them in certain places. It adds the systemd service entries and things like that. Basically configures the virtual machine to be an automated control plane node, to where if it were to shut down and boot back up, everything comes back on as expected. It's also building up the Kubernetes objects that have to run. So one of the things when running behind the scenes of Kubernetes, there's a lot of different components that run. You've got the actual kubelet itself, but then you've got the API server, the scheduler, you've got your network overlay. There's all kinds of stuff that's going on behind the scenes. So we don't get a real good visibility into that just because it's kind of scrolling by, but that is what's there. So yep, it just finished, and we can see it moved on. It also grabbed our kubeconfig, which is this YAML file. It pulled that off of the control plane node because that's one of the artifacts that gets created as part of that. And it's now creating the worker. So we can see the worker starting up here. It's going to assign it to the Harvester node and then begin booting the actual VM. Now, workers, when running and installing, there is far less for them to run. Generally, they are just a kubelet, and then they have the network overlay and they're done. They do not have like the kube API server and things like that. I won't dive into too much of what those are, but that's generally just what stuff runs on the control plane. So workers are simpler. They're more for running workloads as opposed to, maintenance and management type utilities. All right, so it detected that the worker VM now has an IP address, and it's moving on to inspecting and waiting for Cloud Init to complete. So once Cloud Init completes, it's going to move into installing the Helm charts. And the first one is Cert Manager. So if you've ever installed Rancher by itself, you know that Cert Manager is a dependency. And so we install that as a Helm chart. And that Helm chart, again, we have referenced locally as a tarball, but if you are in the cloud and you're not on an air gap, you can actually pull those from the cloud, much like you do with a Git repo or an image or something. Helm's really cool. All right, so the VM is now done. It is up and running. Cert Manager is installing. Generally doesn't take real long because all the images are available in Harbor, and it's done. 27 seconds, not half bad. Now it's installing Rancher, Rancher Cluster Manager. In this case, we just call it Rancher Server for the release name. This one takes a little bit longer just because there's a lot more stuff that gets stood up. So one of the ambiguous bits here is Rancher, commonly referred to, is a lot of times when people say Rancher, they usually mean the Rancher Multi-Cluster Manager, or MCM. It's the single pane of glass that allows you to manage many downstream clusters, regardless of environment, and also manage the applications and metrics and observability that go on and come off of them. So that is the Helm chart that's installing here. So once that is finished, one of the things that I'll be moving through pretty quick that might affect you and your environment is the DNS assignment. So Helm, or not Helm, Rancher under the hood, we are using, oh, it's finished, cool. So the whole run took 6 minutes and 20 seconds. That ain't half bad, which is right here. So under the hood, what happened when Rancher got created is it created what's called an ingress. And an ingress is basically a layer 7 load balancer of sorts. So when your packets come in, you have your host name, and you've defined a host name request saying, brianswebsite.com / some values. Those values, the URL and the values that go with the whole URL, they can be rendered in different ways and route the packets accordingly. So you can have many different systems running behind the same IP address, but based on the URL that was fed to it, those packets can get routed to different endpoints, which is one of the really cool features of layer 7 load balancing. In this case, I'm using rancher.home.cnr Fleet Systems, which is my little Star Wars joke. That is my URL. If we go in, I'll go ahead and add it. Well, that IP address, or that DNS entry is being resolved to an IP address. And because the ingress is running on top of the RKE2 cluster that we just created, that RKE2 cluster has a static IP because that's what I used for KubeVip. It is, in this case, we can go look at the values over here in my variables. It is 10.10.5.4. That's the IP address. So my DNS that I also configured, I have this defined in my travel router. It's not technically DNS, it's a hostname override. But when I actually try to do a resolve of it, it just shows 10.10.04. So we'll do a NS lookup here. And there it is, 10.10.5.4. So what I'm going to do is now hop in. This is where my Rancher actual dashboard should be running. And we'll just override the Terraform stuff here and go straight there. So I'm using self-signed certificates in here. You don't have to. There's plenty of mechanisms to inject your own. For my conference demo that I have normally, I normally do have actual full certificates. But in this case, in the demo, we're just creating some self-signed ones. Google's trying to protect us from ourselves, so I'm going to bypass it. And if you don't know this one's kind of a cool thing. If you see this, your connection is not private and it won't let you go by. If you type in the words, "this is unsafe," it will bypass it. Kind of a cool feature. So my bootstrap password that I put in there is just admin. I'm going to let it use the generated password because I'm going to throw this environment away later. I'm going to hit continue and give it a moment. And then here we are, the Rancher Multi-Cluster Manager dashboard. One of my favorite places to be, just because there's so much stuff that you can get into here. In this case, we've now installed Rancher on top of our RKE2 in an air gap environment with all of our Harbor images and things like that all defined within kind of self-sustained. I could disconnect this environment and run this whole thing again, and then everything would work. But in the essence of being able to share stuff and reach things, we're still got a little bit of internet access. But it works well. One of the powers of Rancher Multi-Cluster Manager is the ability to provision downstream clusters as well as import existing downstream clusters from other infrastructures, so you can pull them in from other manufacturers that maybe we don't have a provisioner or node provisioner for. You can still manage those environments just fine from the same console. All right, so the last aspect that we talked about. Harvester is also an infrastructure to deploy downstream clusters. So from Rancher purposes, we have to know where that Harvester endpoint is. So Rancher has a built-in virtualization management, and this is for importing existing Harvester clusters. So I'm going to create one here, and I'm going to call it Harvester. And what it does is it gives me this command that I can actually run against my Harvester or place into my Harvester configuration. So I'm going to go to Advanced under Settings, and it tells you where to put this. I just have this memorized, so don't worry too much if you're not sure. So I paste it in here, and this is literally just a command for it to run. And it registers, Harvester being it, registers with the Rancher Multi-Cluster Manager, and we'll see it pop up here in just a second. There it is. And then once that management cluster line goes green, then that means the Harvester cluster can now be used as infrastructure, or one of the infrastructures that this Rancher instance could deploy to. So theoretically, we can deploy to AWS or Azure if we had full cloud connectivity, or if we were in an environment where we had a vSphere running, we could deploy there too. The sky's kind of the limit. So I'm going to create a cloud credential. And if you don't create one, it'll ask you to create one. I'm just doing it ahead of time. So Harvester. And then I'm going to add my cluster here and hit create. All right, got a cloud credential. So now I can actually come in here and we can create some clusters. Switch over to RKE2, Harvester. And then here is where I would actually create a Harvester cluster. I could call it test and then give it some machine counts and then some CPUs, that's all fine. Notice it's auto-filling in all of my namespaces and stuff like that. And there's my images that it found too. We'll put it on Sandbox. And then Ubuntu is the user. And I'm going to switch the version to a little bit older version that is in my Harbor registry. And then everything else is fine. Now, I'm not going to spend too much time watching this because we're just about out of time. But what's happening is it's going to try to create a downstream cluster into the Harvester infrastructure. So it's saying, yep, 3 machines. It's waiting for some stuff to happen. We can actually come in here and dive in and see which each machine is trying to do. It's saying creating server. So let's go verify that. Look at virtual machines, and oh wow, there's 3 virtual machines that it's now attempting to create. This takes between 5 and 10 minutes to come up, so I'm not going to show that here, but this is how you would manage clusters downstream through the UI. You can also create them in automated ways. We can dive into those in future topics, but that's it. So we've actually provisioned RKE2 and Rancher using Terraform in a declarative way. Starting back with the Terraform itself, we can come in here and we can tweak things to our needs. We can add in more stuff and add in more infrastructure if we need to. But this makes a really good starting point for deploying a RKE2 and Rancher environment in an air gap in kind of a production way. So that's all I got. Let's move on to Q&A, see what kind of questions we have.